Hello, Professor Harjit Singh here, and I welcome you to the exciting world of statistics. Today, we will discuss correlation and linear regression and multiple regression. With respect to correlation and linear regression, we will look at the purpose of correlation analysis to examine relationships between two variables. Thereafter, we will learn how to calculate and interpret a correlation coefficient to measure the strength and direction of a relationship. We will also learn how to apply regression analysis to estimate a linear relationship between two variables. In addition, we will also discuss a few other related topics such as calculation and interpretation of confidence and prediction intervals. For multiple regression, we will investigate how to use multiple regression analysis to describe and interpret the relationship between several independent variables and a dependent variable, and how to apply this knowledge across several other associated topics. Now, what is correlation analysis? Correlation analysis quantifies the relationship between two variables. Numerical measures supplement graphing techniques like scatter diagrams, or what we call scatter plots. For example, it explores how a company's training expenditures affect the sales, or how study time impacts exam scores. This is a great technique for making decisions in business. Uh, in all business fields, identifying and studying relationships between variables can provide information on ways to increase profits, methods to decrease cost, or variables to predict demand. Okay, so again, the underlying mechanism of correlation analysis is scatter diagram. First, we need to draw a scatter plot. A scatter diagram visually represents the relationship between two variables. The independent variable, we call predictor, or which is on the x-axis, and the dependent variable, we call it outcome, that is on y-axis. It helps identify the direction and strength of their relationship. For example, a sales manager wants to know if there is a relationship between the number of sales calls made in a month and number of photocopy machines sold that month, and begins the analysis with a random sample of 15 sales representatives. With this data, the number of sales calls is the independent variable, and the number of copiers or photocopy machines sold is a dependent variable. As you can see, the data is given on this slide. Now let's look at one example of this scatter diagram. I mean, the diagram uses the same data that we just saw on the previous slide. So this shows how this is plotted. You can see the sales calls are along x-axis, and copiers sold are along y-axis. And these data points in this area, in this quadrant, they are XY coordinates. For a given value of X, there is a value of Y. So for various data points refer to various coordinates, XY coordinates, right? All right, so scatter diagram shows that, shows if there is a correlation or no correlation. But if there is a correlation, how strong is the correlation? Okay, how how strong is the correlation? Well, one thing you should know that scatter plots, they measure linear correlation. Okay, either linear uh, positive linear correlation or negative linear correlation, or no correlation at all. So, but if there is a correlation, how strong it is it? So correlation coefficient measures the strength of the linear relationship between two variables. Okay, it could be positive, could be negative. Okay, for example, a manager found an R value. R value is for R is a correlation coefficient. So when you find R value, you're finding correlation coefficient. So for example, if a manager found a R value of 0.865 for sales performance and conducted a hypothesis test to verify its significance. Uh, so, so what the manager is trying to find? Trying to find the strength of the correlation. So we'll see. Actually, there are some characteristics of correlation coefficient. It can vary. First of all, it's a linear. Then the ranges from -1 to +1. Okay, and it measures the strength of the relationship, and it's denoted by small lowercase letter r. Okay, so if the value of a correlation coefficient is uh, 0, there is no correlation, right? So then if it's close to 0, it shows that there is a little correlation depending on which side of 0 it is. If it's toward +1 side, we can say, hey, it's like a little positive correlation. If it's if the value is less than 0, but of course, less than 0 means it's heading toward -1. So if it's close to 0, but on the left hand side, then we can say there is a little negative linear correlation. So this slide depicts what we just talked about. So here is there's two extremes here. This perfect negative correlation, and the other side is perfect positive correlation. In the middle, we have no correlation, and the as we go from 0 to toward 1, the strength of the positive correlation keeps increasing, and as we go from 0 to the -1 side, the strength of a negative correlation keeps decreasing. So I can see that close to 0, we have weak correlation, and in between 1 and 0, or -1 and 0, there is a moderate correlation. And when the value approaches 1 or -1, it becomes a strong uh, correlation. And similarly, the plots actually, they correspond to what we were just talking about. All right, so let's look at how, all this data has been processed. You can see that there's more details here across different quadrants. where you can find the mean values, X bar by Y bar for various values of X and Y, and come to some generalization of that. And finally, when we go through detailed regression analysis using Microsoft Excel, we can find the value of R. The formula is given here. This is the formula if you want to do like manually, but Microsoft Excel can do it for you. So basically, the goal is to find the value of R. So 0.6865 is a positive value and it's very close to 1. So what does this tell us? This tells us that there is a strong positive linear correlation, right? So it's very, very useful tool for decision making. Okay, regression analysis. So regression analysis estimates the dependent variable using the independent variable in a linear relationship. Both variables must be either interval or ratio scaled. The goal is to find a line of best fit. So the line, how we find it via the least squared method, right? Least squared. We will talk about that in a moment. Regression equation, which we actually ultimate goal is to find the regression equation, which we can use to find various values of X and Y once we have the equation established. So equation that expresses the linear relationship between the two variables. That's a regression equation. And we will look at the steps how to develop the equation. So let's look at what least squares method, principle or method is. The least squares principle ensures a best fit line by minimizing the distance between data points and the regression line. Basically, you won't see all the data points perfectly lined up, like either in a descending order or ascending order, but I mean, at least they are showing up such a way that if there is a correlation, that we can draw the line of best fit, right? So, but it's not you randomly draw the line of best fit. We can use this principle called least squares principle to basically we try to figure out actually how to minimize the distance between the line and the points across above or below this line we are trying to use. Okay, so and so the sum of squares method is used in a scatter plot analysis to measure the variation of data points from a trend line or this line, typically in a regression analysis. So we can look at this example here. Say, let's say there is a scenario that we are analyzing the relationship between our studied and exam scores for a group of students, hypothetically speaking. So we have two data sets here. One is one data set for X, which is independent variable. No, sorry, independent variable, and Y exam score. Exam score we can plot alongside of Y axis, and that is a dependent variable. Y is a function of X. So let's say one set of values like a XY coordinate is 2 and 50. That means if somebody studies 2 hours every day, has a score of 50. Okay, let's look at one set of values. So what we need to do here is, so we have a one value of X and Y, and we can use scatter plot. So we can use scatter plot, pick those values, and we create a scatter plot with our study and on our study on x-axis and exam score on y-axis. So then we can create a trend line. Trend line y is like mx plus c, or some people call it y is equal to ax plus b, where b is b a is the coefficient of x, and b is a y-intercept, where the line intersects the y-axis. So so we can have that. Actually, we can use this value. So y is let's say, hypothetically speaking, we have y is equal to 5x plus 40, right? So in this case, we can use some of Scare's method. What we can do is we need to look at, okay, what is the predicted score from the trend line. If we use this trend line, like a y is equal to 5x plus 40, and then we also once we find that predictive score from the trend line or line equation of the line, and we can compare that value with what is given to us in the data, right? The actual value. And once we have that, we can take we can what we can do is we can it's called let's see, some least square method. So basically we have to um, take the difference, right, of the two values we have. So we have actual score, we have predicted score. So there may be difference, there may not be difference. The ideal situation we are looking at is like a least difference. So so in this case, when I plug in the values here in the equation, what I find is like the y is equal to 50. And that's a predicted value based on the trend line. But the given value, or actual value of the score is also 50. So what is the difference? It is 50 minus 50 is 0, which is great. So when we scale it again, 0, right? So we repeat this. I mean, for other XY coordinates also in the data set, and this is how we find the values that we need to draw a line on, right? So it's called a least squares principle. Okay. All right. So these lines are, I can show you an example of those. Yeah, so these are again continuing with that. The principle I just described you is a continuation of that. These are charts here show the various ways. There are different ways to draw the line. This one is the least squares line. Then it's a line with a straight edge. So this is straight edge. Basically, you're connecting the edges, whichever makes sense here. Then here we have the least square line, and third one is a line drawn with a straight edge. All the top of the edges, they are connected of for various points, right? So different ways of doing things, but I'm saying the best approach is to use least squares line, as we just talked about. So the equation of the line, is, this is the equation of a line. So remember this, this is the general form of a linear regression equation. Y, people call it y hat or y itself. Um, Different literatures, they use different notations. So is y is equal to a plus bx, right? So where a is the value when we have all the variables set to 0 in this case, and the intercepts are 0, 0, 2. So basically, we can find the value of a from this equation, and if it's not given, if it could be given also, right? And so in this case, y is equal to a plus bx. B is the slope of the line, and a is the a is the y-intercept. A is the y-intercept. Let's say if we set the value of x to 0, then we get y is equal to a. That means for a value of when x is 0, then what is the value of y? That means where does this line intersect the y-axis? Okay, so a in the equation is the y-intercept, and b is the slope. Slope, for line, you can find the slope by uh, using rise over run relationship. Like for example, the slope of this line is like you draw the horizontal line here and draw the vertical line here. It kind of becomes a triangle. The slope is hypotenuse of this little rectangle. Then you can use the trigonometry formula here, rise over run. That can give you a slope of the line, which is in this case is b. Okay, so b can be found here, and then you know what the slope of the line is, and the already know the y-axis. Then you can get a line like this. So line equation of a line. So once we have the equation of a line, we can use this for various to find out, okay, for various values of x, what is the corresponding value of y. And the slope, again, as I said, slope of a line, which is given by this formula, b is equal to rise over run. Rise means sy, and run means like the value as x changes, the sx. So r is the correlation coefficient showing the strength. Y-intercept can be found by this rearranging this equation here. So it's pretty useful equation that can be used to do any kind of regression analysis using the least squares regression principle. All right, moving right along. Oh yeah, so there is another example. Actually, this example shows how to use this line equation of a line to actually in a real life scenarios here. So we can use this to let's see. This one is yeah. So this is the same example that we have been using for our discussion. So if you go back to one of the previous slides, you can find this s value of the sy and sx, and also the correlation coefficient. If you remember, we just saw that before. We can use these values to plug into the equation um, and solve it for our use. So we can going back now. So going back now, and in this case, if you see that we had the value of r 0.865, and also when we did the regression analysis, it gave us these values here. These are highlighted values for sx and sy. We can use these in the equation, and we have here is we can plug in the equation and we find the value of b slope. What we need is the value of b for slope, and a, and we know this relationship for a, and we can plug in these values and to find a, and we got the value of b and a. That's what we need. So there, once we have these, we can just create our equation here. Y hat is equal to this equation. So basically, once we have this all set, so we have a recipe ready to cook the dish, basically. So we can, now we have one independent variable x, and we have dependent variable. So we keep other things that are constant. I mean, constant means like numerical values. So we can change the value of x, and we can get the new value of y for every changing value of x. So basically, in this case, one example here: if salesperson makes 100 calls, then how much he or she can sell. So by we put the value of, I mean, 100 calls, number of calls are what? Number of calls are on a x-axis, right? Number of calls on x-axis, yeah, sales calls on x-axis. So that means those are values of x. So x is equal to 100 in this equation. It gives us y equal to 46.0432 copiers. Um, so that way we know that if a person makes 100 calls, then he or she is expected to sell about 46 copiers. Pretty interesting. All right. So we can use this mechanism to look at various values of x and finding the corresponding value of y. We already know, actually we have these values here given here. They are given, copies sold y. This is given value, but we can also these are a given actually, but this data but we can find the predictive values also by using this equation. So and we can plot it. This is the prediction line. It's like a, you can plot this line, and we can predict, like a, regardless of this data is given here for whatever the actual data was captured. But I'm saying based on this trend, say, hey, this is great for forecasting. What is a forecasting? Forecasting in a statistics is that nothing is absolute. Actually, we know how we know what's going to happen in the future. So that we can only tell if we know what's happening in the historically before before today. So and we say, hey, if this trend continues, then what will be the future? So that's why the beauty of this trend line is to predict the future for decision making. So we have some data given and we understand it, and we're going to use this data to develop a trend line. And then for any given value of x, we can find value of y. And that's what we need to make a prediction. So let's say I say, hey, if somebody makes like 1,000 calls in a day, how many copiers? So basically plug in the value of x and find the value of y. And for various values of x, you can find corresponding values of y. Very great, maybe great tool for statistical data decision making. And also we can also, what we can do is, we can do the slope test also to make sure that I mean, it's not like a whatever we predict is gonna be like exactly correct, but there may be, but thing is we can do some testings to just verify how good our prediction is. So the slope can be tested for significance. um so regarding the correlation, basically, so what we can do here is the slope of the regression line equation shows how much the dependent variable changes with the each unit changes in the independent variable, which is x. A hypothesis test can determine if this slope is significantly different from zero. Okay. If you look at this kind of a scenario, this is a one-tailed test. If we do not reject the null hypothesis, we conclude that the slope of the regression line could be zero, right? Could be zero. We can use Excel to determine the. But before we do that, actually, first of all, let's look at actually how we do this. Um, So we have to first state our hypothesis here. We can use null hypothesis as beta is equal to 0 and alternative is not equal to 0. So this is very simple setup for slope testing to show that if there is a relationship between the two variables or not, right? But now we can apply this to actually in an actual situation, that the same example that we have been talking about, North American copier sales example. In this case, we can set up a hypothesis test for slope test. So we can, all the steps, step 1, 2, 3, 4, 5, 6. Step 1 is we state the null and alternative hypothesis. So H naught beta is less equal than 0 and beta is greater than 0 is a alternative hypothesis. And let's say we have a level of significance. If it's not given to us, we can assume this is 0.05. And now we have to primarily what we're doing is using the test status. We're going to use a t-test here, you know, and whenever we have a inequality sign in our hypothesis statement, we use two-tailed test. Two-tailed, no, sorry, I'm take it back. One-tailed test. Sorry, my bad. One-tailed test. If we have just equal or not equal, then we use two-tailed test. In this case, is less equal or greater. We use one-tailed test here. Okay, so and we use t statistics here, and how do we find our critical value for this? So we can use the critical values table for one-tail test here. This is something I found on internet, little table here that I used here. And these kind of tables are available in the back of any statistics book, or you can find them on Google by searching it for them. So on one side we have degrees of freedom here, and then we have the level of significance. In our case, we have a level of significance 0.05, and the degrees of freedom we have what do we have is 13. So total items in the data set we have 15, and degrees of freedom equal to n minus 2, which gives you 15 minus 2 equal to 13. So we are using those, and to find the value where the rows and columns meet, we have this 1.771. So now, okay, this is our critical value, and we need to find the actual value of t. So we compare with the 1.771. Okay, then we interpret. So the decision in step number 5 is that reject null hypothesis if t is equal to 6.205, right? So then we interpret. Okay, first of all, we can find the value of slope by using this formula, and degrees of freedom by n minus 2, and we can find the slope, which gives us 6.205. Okay, and we can also use Microsoft Excel to help out with the finding the value of b, and b a plus xb. Fb is the slope of the line, and standard error. So how we evaluate a regression equation's ability to predict? As I said, prediction is prediction. It's not like always like a gonna be coming true, or there may be variation, plus minus variation, and we call it standard error of estimate. Okay, So again, in the world of statistics, there's nothing absolute. Everything is like a best estimate. So while regression equations provide estimates, they may not always accurately predict individual outcomes. And as I said, the standard error of estimate helps measure prediction errors by calculating the variance around the regression line. Okay, so we can use that, and for example, here in this case, the example we are following that if we use the equation actually that we have number of copies sold, and we can but once we solve it for sales call 84, let's say the sales call were 84, and that will give us from the equation the number of copies sold 41.8704. But the data set that given to us says that the two people who actually made 84 sales call, they sold only 30 and 24. Our prediction is saying 41, which is far off, right? So what we call it this scenario. In this case, what we are looking at here is, we are observing what we call is standard error of estimate. Okay. So standard error of estimate, we can use the formula here for that. Although Microsoft Excel can figure it out for you, but this is the formula that can be used. And here is the definition of a standard error of estimate that a measure of the dispersion or scatter of the observed values around the line of regression. Basically, line of regression is the ideal line of prediction, but it may not be the reality may not be the same. Okay, maybe plus minus. So here's an example of a standard error of estimate that we have been talking about. You can use Microsoft Excel, and that will give you, as I said, they give you standard error of estimate. In this case, with the data we have been following, using that all along, we have it. This is as 6.720. So as you can see that even if you go back here, let's see, if you subtract, let's say 7 from 41, it gives you 30 34 or so. So basically, and that's roughly the standard error of estimate, that that you can account for the difference between predictive values and actual values. Now let's look at the coefficient of determination. So coefficient of a correlation is R, but coefficient of determination is R square. Okay, so while regression, no, I mean, say well, how well the independent variable explains the variation in the dependent variable. Okay, so that's we have been looking, we have been using the value of R, right? So, but it gives you better idea about the correlation compared to just coefficient of correlation. All right. So an R, like for example, an R square of let's say 0.748 indicates that 74.8% of the variation in the copier sales is due to sales calls. Okay. Let's see this example here. Again, coefficient of determination varies from 0 to 1. You obtain this by squaring the correlation coefficient R, and the formula for that is this given here, coefficient of determination, uh, R square. This is the formula for that. And remember, this R we found before was 0.865. We square it and gives us 0.748, which is better estimate actually compared to simply R. Okay. So now you might be wondering, what is SSR? What is SSE? SSR stands for regression sum of squares. So SSR represents the variation explained by the regression model, and it measures the difference between the predictive values that we get from the regression equation and the overall mean of the actual data. Okay. And how about SSE, or its error sum of squares? Error sum of squares measures the unexplained variation, unexplained variation or error. It captures the difference between the actual data points and the predictive values from the regression line. Essentially, it quantifies the deviation of the actual values from the predictive ones. Then we have SS total. SS total is a total sum of squares. So when we add these above two, SSE and SSR, what we get here is SS total. SS total represents the total variation in the dependent variable. It measures the difference between the actual values and their overall mean. Okay. And then we can use this to, all in combination to find a coefficient of determination R square. Now, how we interpret the value of R square? Okay, simply put, if R square is equal to 1, the model perfectly explains the variation, this model. What if the value of R square is 0? Then the model doesn't explain any of the variation. And if it gives you value between 0 and 1, whatever, so that's what we are talking about here. It gives you the information which is very very accurate. So a 0.748 value means that 74.8% of variation in the number of copiers sold is explained by the variation in the sales calls, right? So that's called coefficient of determination, R square. Okay, how these all these parameters are related? There's again, as I explained before, correlation coefficient is measures the strength of the linear association between the variables, two variables basically, and um, then the R square actually gives you provides you better prediction. All right, so what is this confidence and prediction intervals? How we So these are formulas that you see here. Seems like a little complicated formulas here. Confidence interval for the mean of y given x, and then it's a prediction interval for y given x. A confidence interval estimates the mean value of y for a given x. Okay, while A prediction interval estimates the value of y for an individual observation. So why we use these? We use these to assess the reliability of predictions. Okay. So let's see, for example here, it says that we would use a confidence interval to estimate the mean salary of all executives in the retail industry based on their years of experience. If this is the kind of scenario, right, where we are trying to use the mean value, right, then we use a confidence interval, like basically around the mean. Now, other scenario here is we have estimated the salary of a particular retail executive, sorry, who has 20 years of experience. So now what we need to do is a prediction. So we are trying to do prediction, right? Then we use the relationship that is given in this equation 13-12. And we can, the example that we have been following, we can use that to actually solve the real example. Okay. Okay. So I was saying, yeah. So we can use apply this understanding to solve the problem that we have been following along. In this scenario of our American copier sales. Okay. The scenario here is determine a 95% confidence interval for all sales representatives who make 50 calls and determine a prediction interval for Sheila Baker. So as you can see that this is a scenario that we just talked about before. So we can use these values, but here we don't have to, I mean, we can do manually also by using the formula, but again, you can use Microsoft Excel also for that. All right, so transforming data. What happens is why we need to transform data. If the data is non-linear, so this data may not be linear always. If data is non-linear, we have to use transformations like logarithms, square roots, reciprocals. Um, they can help us make our relationship linear. So that will allow us for a more accurate correlation and a regression analysis. Very, very useful. It's like just like coding and decoding something. So let's take a look at it. How we do that. There is an example here. Actually, we can use this to see how it is. So you say Grocery Land Supermarkets is a regional grocery chain located in the Midwestern United States. The director of marketing wishes to study the effect of price on weekly sales of their 2-liter private brand Diet Cola. The objectives of the study are to determine whether there is a relationship between the selling price and weekly sales. Is this a relationship direct or indirect? Is it strong or weak? Number two, to determine the effect of the price increases or decreases on sales. Can we effectively forecast sales based on the price? Okay. So we can actually get some data to work on this problem. So what we can do is say, let's say the company decides to price the 2-liter diet cola from various prices from 50 cent to $2. Okay, so a random sample of 20 stores is taken, and then each store is randomly assigned a selling price. Okay, let's all look here. So now, after we complete that exercise, we have this data set here. Okay, see the yellow highlighted data set. We can plot it. Well, so we can use this to, so we can use this to do the regression analysis here. It shows that there's a strong inverse relationship. Okay, so what we have here is we have this. You can see this here, like we can use any statistical tool to or Excel to achieve this. Now, what we have here is if you see this step number 1 here. No, sorry, here. So this one is what she said. The director of marketing decides to transform the dependent variable sales by taking the logarithm to the base 10 of each sales value. The new variables using the long scales. So basically trying to improve the prediction. What the director is trying to do is transforming the variable. So the dependent variable is sales. So the coefficient of determination was 0.889 given by this software when we use the regression analysis here. So taking the log of we can use to take the log of that. So we change this to so now so once we transform the data, then the transformed data fits better as far as the linear relationship is concerned. So basically improves the fitness of the line through the data points. Okay, so after doing that, our equation actually becomes y hat is equal to 2.685 minus 0.8738x. So this equation now we can use. Basically, this is based on the transformed data. Okay, so based on that, we can use, like, for example, hypothetically speaking, we use the selling price of $1.25. We get what we get is 1.593, right? But how we translate that into the actual sales? So we take a anti-log of this value. It gives us 39.174. That means 39 bottles. So how we interpret this? We interpret this as saying that, okay, if we have the price of the bottle set at $1.25, then we are expected to sell 39 bottles. What if they increase the price of the bottle to $2? That's the max price allowed. Then we only sell 9 according to this equation. So it's a really good way to improve the quality of reliability of our predictions by transforming data. Well, multiple regression analysis. Here we have multiple variables, not only like simple regression analysis is like a relationship between two variables, x and y. But in this case, we have y is of course the independent variable, but we have x1, x2, x3, and a number of more than one number of uh, independent variables. Why is dependent variable? Sorry. Okay. And this type of equation is basically enhanced version of the equation of a line that we saw earlier for a regular line of uh, regression. So A is a intercept, that's y-intercept. B is refers to the sample regression coefficients. So various values of V1, V2, V3, V4, and so on. And X1, X2, X3, they are all actually different independent variables. So we can use this for our multiple regression analysis. Here's an example that we have. Example says, so suppose the selling price of a home is directly related to the number of rooms and inversely related to its age. Okay. And let X1 is the number of room, X2 is the age of the home, and Y hat is the selling price in thousands. So, well, the directly related means, okay, that means we use plus sign, right? Inversely related, we use minus sign, right? So Y hat is equal to 21.2 plus the B value. Just like for now, just assume these values we already have them. Okay. All these values of B1, V2, V3. And we create this equation like this. Now, we know that value of x1. So for a given value of x1 and x2, we can find the price of the home. So this line here, you see this y hat is equal to after putting the values in, it gives us 144.6. So 7 here means the 7-room house which is 30-year-old. Okay. And in that case, this house is expected to sell for $144,600. Okay. So we can use, when we have multiple factors to consider, you can also say a multi-factor decision making. Multiple factors to consider, we can use multiple regression analysis. And we can use this, the we can use this for various scenarios similar to that we just talked about by using Microsoft Excel is very powerful for that. You can use Microsoft process, Excel. Here's another example saying that here is example. It's pretty interesting example here. Yeah, it says Salisbury Realty sells homes along the east coast of the United States. One question frequently asked by prospective buyers is how much can we expect to pay to heat the home in the winter? The research department of Salisbury thinks 3 variables relate to the heating cost: the mean daily outside temperature, number of inches of insulation, and the age in the years of the furnace age. And they conduct a random sample of 20 homes. Now, we need to find a regression equation. Well, in this case, it's a multiple regression type of analysis. We know that this kind of data, we can use this data obviously given to us. y is a dependent variable, x1 is outside temperature. Okay, let's say x2 is inches of insulation, x3 age of the furnace, and we can create an equation. So y hat is equal to a plus b1 x1 plus b2 x2 plus b3 x3. Okay, so now our model is all set. So we can now use this data to see what we can find. So, all right, so here we can, we can be given any values of x1, x2, x3. Like say in this case, we are given for January. So we look at the data here, month of January. So for January, let's say we have outside temperature 30 degree and 5 inches of insulation, and the furnace is 10-year old. We can use those values in our equation here, and it gives us $276.56. So basically, what it gives us is that estimated cost of heating in January is $276.56. Because here, we are considering multiple factors that can, affect the cost of heating. All right, so we can use ANOVA analysis also. ANOVA, we analysis of variation. ANOVA is analysis of variation, and analysis of variation. Sorry, variation. Analysis of variance, not variation. Analysis of variance. ANOVA. Those tables, as you can see here, right? This one formula is here. They summarize the table. This summarizes the multiple regression analysis. So ANOVA divides the total variation into two parts. Number one is regression. That's explained by independent variables. And number two, residual or error, which means unexplained variations. So ANOVA tables, ANOVA tables use degrees of freedom, regression sum of squares, and residual sum of squares, as you can see right here. Okay. We can use, we can look at this parameter multiple standard error of estimate. What we're trying to do here is measuring, measure effectiveness. Okay. The two measures evaluate how well the regression equation fits the data, how effective it is. Okay. So one key measure is multiple standard error of the estimate. It's similar to standard deviation. It measures the variation of the actual values from the predicted values. How we interpret those? Smaller values of multiple standard error of the estimate indicate a better fit. Second key measure is coefficient of multiple determination, R square. This indicates the percentage of variation in the dependent variable explained by the independent variables. It ranges from 0 to 1. With and how we interpret any given value. So the higher the value, the closer to 1, the higher the stronger is the relationship. Well, you can use um, Microsoft Excel is a great way to do ANOVA analysis, right? You can find multiple standard errors of estimate for any data set you have, and you can find coefficient of multiple determination, and and a coefficient of multiple determination R square. So R square, we the formula which is R square is equal to SSR divided by SS total. So all these you can do by using Microsoft Excel. Continuing with that, and all these are similar. I mean, along the same lines that we can apply to our example of heating cost per home. All those scenarios we discussed, actually, we can apply ANOVA analysis to that also. Finally, we need to look at the global test. What is global test? The global test estimates whether the independent variables collectively influence the dependent variable. The null hypothesis is that all the regression coefficients are zero. That's a null hypothesis initially. That means we go with the assumption that that there is no influence basically of the dependent variables on the independent variable. So we have to either refute this hypothesis or null hypothesis or accept it. So alternative is not all betas are zero. We go with the assumption that they are zero. So in this case, what we do here, we have to use F distribution with the F statistic. Okay. And we know from this F distribution rules that it cannot be negative. It is continuous, it's positively skewed, is asymptotic. Means that it has a bump in the beginning, then it just goes all the way. Sorry, no, I'm sorry. Asymptotic means that it approaches the distribution curve approaches horizontal axis, but never touches it. It keeps going all the way to plus infinity. So it's a similar to what we have been, there's a standard way of using F distribution. So what we need to find is you can use ANOVA analysis to find degrees of freedom. Then we can find F statistic by using this formula here, where in this K formula we have K. K is the number of independent variables, right? Degrees of freedom in the numerator. Okay, so degrees of freedom in the numerator, right? That so there are in when we use ANOVA analysis, remember? No, sorry, F distribution. We need in F distribution we need three pieces of information: the numerator degrees of freedom, the denominator degree of freedom, and the significance level. So here, so K signifies degrees of freedom in the numerator, and n minus in parentheses K plus 1, those are for degrees of freedom in the denominator. N is a sample size. So we can do ANOVA analysis for the data given to us and find degrees of freedom. We need that, right? I mean, so once we have that, we can set up our hypothesis. So step one is we state that in a null hypothesis, that everything is zero, all betas are zero. And alternative hypothesis, not all of them are zero. So, and the level of significance we use again 0.05, and we have to use a F test statistic. Now, the decision rule we have is reject H naught, which is a null hypothesis, if F is greater than 3.24, which is a critical value here for F. But we have to compare the actual value we find with the formula against we compare with the 3.24 and see what we get. And so what we get is F value, the actual value of F using the equation we found is 21.90. So how we interpret this? So it says that this null hypothesis is not true. Okay, that means at least one of the independent variables has the ability to explain variation in heating costs. So there is a dependency. We can't say that none of the independent variables they have any they have no effect on the independent variable. Sorry, dependent variable. Okay, so they do affect at least one of them. So in nutshell, we can say the global test assures that one of the parameters like outside temperature, amount of insulation, or the age of the furnace, okay, one or more of those, they can affect the heating cost. So that was a global test for multiple regression. That concludes our discussion for today on linear correlation and multiple regression. Pretty intensive, but I hope you enjoyed it. And looking forward to talking to you again in another session, another time. Thank you so much for your attention. All the best.